for the demeanor. If there's any kind of errors, I'll make it a point to go back and kind of remedy my situation, but I wanted to kind of go through the information on it. So let's go ahead and get started. First of all, when you understand chemistry, it is the study of nature and all things that deal with the transformations of matter. Matter represents anything that takes up space and has mass, so you matter because you are made of matter. We won't go into extensive detail about the scientific method, but it is important to understand it as a fundamental unit or process that is applied in our lives, both in science and our everyday practical applications. I will not extend much detail further on it because this is just kind of a proof of concept thing. Now, for chemistry, you're going to have to emphasize understanding this thing about properties. Now, properties are characteristics that can be used to identify various chemicals, and they're identifiers. We're going to be looking at many of the properties as they pertain to both the physical and chemical nature of chemical components. Now, when we talk about chemistry in itself, we're talking about the rearrangement of atoms to form compounds, and that doesn't always occur. Sometimes when that does occur, we look at that as a chemical reaction, and yes, that is a chemical reaction, but it also can be representative of a chemical change. In that case, you have one atom arrangement that changes into a new atom arrangement. Alternatively, we're referencing physical changes. When you think about physical changes, it doesn't change the chemical makeup of the chemical in question. For instance, the transition between water to ice. That is a physical change, whereas a chemical change might be referencing the reaction that occurs when you use fireworks. And so we'll be looking at that as we go further. Now, matter, as it exists for this course, is based into solid, liquids, and gases. And they're broken down that way with specific emphasis on their shape and their volume. Now, with solids, they have a definitive shape and they have a definitive volume. That means it exists as that specific shape and that specific volume. Conversely, when you think about liquids, while they have a specific volume of space that they occupy, they can actually assume the identity of what container they are placed into. So they are deemed to have a specific volume, but not a specific shape. And lastly on this list is gases. Now, gases have neither a definite volume nor a definite shape. And one thing that will come up later is that gases actually exhibit a unique ability to exhibit the highest amount of compressibility. Compressibility means it has the ability to be condensed into a very small form. And likewise, it can be expanded to a very large space occupancy. Of course, that would mean that the atoms are more spread apart. But we'll get into that more when we talk about gases later on. Now, these transitions between these states of matters represent changes of state. They undergo phase changes. You need to understand as a basic premise that when you talk about ice, it represents the transition from a liquid to a solid. When you're talking about freezing, when you're talking about melting, you're talking about a solid becoming a liquid. When you're talking about evaporation, you're talking about the process of going from liquid to becoming gas, etc. But these changes of states represent those transitions between the three states of matter that I mentioned before: solid, liquid, and gas. So, as I mentioned, we talk about melting. You want to know that melting exists when you have a solid becoming a liquid, freezing when a liquid becomes a solid, boiling when a liquid forms a gas, and condensation when you go from a gas to a liquid. And all of these are dictated by temperature. Temperature plays an invaluable role. Now, we're going to be talking about the differences between pure substances and mixtures. Pure substances have a uniform chemical composition, whereas mixtures can represent a blending of two or more substances. In a homogeneous mixture, the uniform mixture is more consistent throughout, and therefore the composition looks very similar. It's not easily discernible what is actually inside of that homogeneous mixture. For example, if I mix apple juice and orange juice together, that would be considered a homogeneous mixture. If you talk about heterogeneous mixture, it's something that's not as uniform. For instance, when I think of a box of Raisin Bran cereal, you have your bran cereal and the raisins themselves. Now, these are uniquely different from pure substances because pure substances have a uniform chemical composition. That means on a subatomic level, they have the same atoms that are used to rearrange or to arrange them consistently. For instance, water is a pure substance. It's uniform throughout as being H2O. Now, looking at the classification of matter further, we have pure substances being classified further into two specific groups. They are the element, which cannot be broken down chemically by any means into a similar substance. And then you have your chemical compound, which represents a pure substance that can technically be broken down into simpler, smaller chemical reactions. Usually you'll have arrangement of elements combined together to form a chemical compound. And those are those two pure substances. Now, in any chemical reaction, as we go through, you'll begin to understand that there are two components that are participants. There are the reactants that are fused together to later form the product. You can't have one without the other. And so the chemical reaction represents that process. For instance, if we look at water, water can chemically be changed to form its representative elemental components. As I alluded earlier, water represents a pure substance, and a pure substance in this case, it is a chemical compound that can be broken down into its smaller units. Now, what we'll be talking about later on is how chemists go about representing these chemical reactions in kind of a shorthand form. Now, another thing that stands out when we learn about chemistry is the serendipity of chemistry itself. Essentially, even though there are a lot of great minds that contribute to chemistry, one of the interesting things that I find fascinating is the fact that a lot of times there can be pure luck that plays a role in the discovery process. Aspirin is one such reference. A more vernacular reference might be in that of Viagra, which essentially was one of those chemical compounds that was initially focused on treating hypertension, high blood pressure, that kind of thing. And as a byproduct, they noticed that such and such happened. And therefore, they used that as a marketing strategy, and thus we know it as what it is used for today. Serendipity refers to the fact that sometimes breakthroughs come by just happenstance. So that's another facet of chemistry that's very fascinating and interesting. Now, one of the things you need to know is that there are 118 chemical elements. That number can actually expand because scientists are always looking to create new novel element compounds that don't naturally exist but are able to be placed on the periodic table. They're usually indicated on the periodic table, which they use an abbreviation using a one-letter or two-letter indication for it. Certain examples might include sodium, and its two-letter is N and A. There are a list of elements that should be known or focused on memorizing as it pertains to the periodic table, because a lot of those are kind of gimme early ones, but a lot of them have Latin origins, and if you ever want to investigate them, the information's out there. Now, what we use for shorthand form is chemical formulas. This is used to represent the expression of elements combined together to form chemical compounds. Subscripts represent those smaller numbers that are used with chemical formulas to represent those chemical formulas, and they can be used to indicate how many of them are in there. For instance, when we look at this first example, H2O, representative of water, there are 2 hydrogen atoms and 1 oxygen atom. The same can be said about there being 1 carbon, 4 hydrogens in methane, and so forth and so on in the case with this compound here. Now, the chemical formulas are used in writing chemical equations, and they are a shortened, abbreviated form for convenience. They also paint a better picture of trying to write the extended form of a chemical formula for a compound. Now, as far as the periodic table is concerned, you want to be familiar with a lot of the elements, but you also want to be familiar with their grouping. As you can see here on the periodic table, they are divided into 3 groups. They're metals, nonmetals, and metalloids. Now, the three groups that you want to know about are going to be distinguished by certain properties such as conductivity, malleability, and things of that nature. But one thing that characteristically helps with memorizing that is just understanding that there's a division right here in kind of the step ladder fashion that separates the metals from the non-metals, and then the metalloids fall right in that middle. And you got one example of a non-metal all the way over here, but that's your one exclusion that you want to group with the rest of these guys. And so let's look at those properties. For instance, metals are very lustrous. They reflect light. They're good conductors. That means they conduct electricity and heat really well. And they're malleable, meaning they can be shaped and adjusted as needed. Now, non-metals, conversely, are going to be poor conductors. They're actually going to be brittle and solid, and there's a smaller group than the metal group. And in the middle between both of them are the metalloids. Now, the metalloids exhibit similar characteristics to that of the metals and the non-metals. That's why they're found in kind of a zigzag fashion in between them. And their properties are very similar. Now, one thing you want to understand is that when it comes down to these groupings, sometimes people ask questions about which one's metal, which one's a metalloid, and which one's a non-metal. And it's good to be familiar with that information. I'll briefly say this about mercury as it pertains to being a metal. It is the only metallic metal that is liquid at room temperature, and it is found in many products. You can find it in amalgam, which is the stuff used in teeth when you have fillings, and it is very dangerous stuff. So if it ever is found in a thermometer and the thermometer breaks, you want to consult your local chemistry instructor or whatever, because mercury can be very toxic and dangerous. Even the vapors can be dangerous. Now, going back to chemical reactions, one of the evidence of chemical reactions lies in the ability of certain changes that are exhibited. We're going to be looking at examples of what happens when you talk about chemical reactions. And while you're looking at that, you want to understand that there are certain features that are evidence of chemical reactions. These evidence include change in color, the dissolution of a solid, or maybe the appearance of bubbles. And while that's evidence in this reaction where you're mixing nickel with an acid, other things that might not be noted on here might be a change in temperature. So a change in temperature could also be evidence of reactions as well. Now, when you're representing a chemical reaction, we write it in an abbreviated form. Now, in the reaction previously shown in the image, they just put simple nickel with hydrochloric acid, and it produced nickel chloride and hydrogen gas. But we represent that using a chemical formula notated down here. This helps with abbreviating the reaction, and it will be useful for other applications of chemistry later on. But the chemical formula is very useful when writing chemical equations. Now, we're going to also look at physical quantities, and we need to understand physical quantities because one aspect of chemistry is heavily math focused, and it deals with understanding units of measurement, and scientists alike have to have a quantified unit of measure that they can use amongst all science. So within this idea, there was the development of a Système International de Units, and my pronunciation is probably terrible, and I apologize for that. It's abbreviated as SI units, but what you want to know is that there are SI units, which are the vernacular units used amongst all chemists. That means that while mass can be expressed using grams and pounds and all these other ways of measurement, the appropriate unit of measure is the kilogram. Likewise, when you're talking about length, the appropriate unit for length is the meter. For volume, the appropriate unit is the cubic meter. And for temperature, the appropriate unit is Kelvin. Time is measured in seconds. Now, what we're going to see as we go through later on is that there's going to be a difference between this unit of measurements and the metric unit of measurements. And you want to be able to discern between the two because questions about that could come around, and it's good to have that body of knowledge. Now, as I mentioned, the mass is measured in kilogram, but the metric unit is the gram. Length is measured in meter, and it's also measured in meter for metric. Volume is different. it is measured in the cubic meter for the units of SI. Now, if you look at the metric system for volume, you'll notice that it is liters. Finally, if you look at temperature, it is different between SI and metric. The metric suggests a Celsius temperature reading, and the SI suggests a Kelvin. This is important to note. There is a difference in the SI units for mass, volume, and temperature. They have different measures going from metric unit to SI unit. So it's important that you understand the differences between those. And my next slide reinforced that concept. Now, the SI units are related to metric units, but they have a few differences. Like I said, the metric unit of mass is the gram rather than the kilogram. 1 gram is equal to a thousandth of a kilogram, 1/1000th of a kilogram. The metric unit of a volume is the liter. The SI is the cubic meter. 1 liter is 1/1000th of a cubic meter. And lastly, the metric unit of temperature is the Celsius rather than Kelvin. And the degree of how that is converted will be shown in a later slide. But essentially, to go from Celsius to Kelvin, you go about adding 273 to the degrees of Celsius to yield the Kelvin measurement. And that's how you get that. Now, there are other derived units, which means units that are extensions of this SI unit of measure. They include speed, which is meters per second, and density, which will probably be discussed later on as grams per cubic centimeter. And they're modified depending on the units measured or what type of chemistry-based problems you're dealing with. Now, another physical quantity that needs to be known is going to be the prefix designation conversions. Now, my focus is usually in the kilo, hecto, deca, deci, centi, milli, micro area, but it is of a benefit to know the other ones. Now, there is a popular mnemonic that people adopt for learning these. King Henry died drinking chocolate milk. Now, the other way is that people go about moving decimal points left and right, right to left, depending on the application. And it really depends on the person. So, that being said, it's important that when you go forward, you understand how to convert between the units, because that is going to be a vital piece of solving problems that deal with chemistry. Being able to identify conversions using dimensional analysis is what it's actually called. So we'll later see some of that stuff, but that's kind of where we are with that. Now, just for establishing mass, because we talked about the unit of measure, mass represents the measure of the amount of matter in an object, and weight is the measure of the gravitational force that the earth on that object exhibits. Now, the difference, even though it's not a big difference, is that gravity affects your weight. Gravity does not affect your mass. Your mass on Earth and the moon is the same. Your weight on the Earth and the moon is different. And that's how those two are different. Now, again, to recap, when we talk about mass, we're talking about kilograms and grams and things of that nature, and it's important that we're able to convert between those units because they can vary depending on the prefix attached. So you want to keep that in mind going forward when it comes down to converting between those units. Now, the meter is the standard measurement of length. We talked about that, and you want to understand that it is used usually using meters. Now, your volume is the amount of space that an object occupies, and that's usually going to be represented using the cubic